If you take a server running one architecture and a laptop running another, they cannot inherently understand each other's data streams. You can physically connect them with a cable, but without a shared rulebook, the electrical signals are just noise. The hardware is connected, but no actual communication occurs. Without a universal translation standard, the global network collapses into a collection of isolated, incompatible hardware islands. The solution is a layered framework. This approach takes the massive, complex procedure of moving data across the globe and breaks it down into strictly isolated, manageable steps. Two major paradigms dictate how this is done: the theoretical 7-layer OSI reference model and the pragmatic 4-layer TCP/IP protocol suite. To navigate modern networks, you have to diagnose problems using the theory of the OSI model while operating within the functional reality of TCP/IP. The Open Systems Interconnection, or OSI, model was developed by the ISO in 1977. It serves as the definitive 7-layer taxonomy for networking. The top 3 blocks, application, presentation, and session, prepare the user's data. They handle formatting, encryption, and establish initial communication. Below that is Layer 4, transport. Here, large messages are broken into numbered segments for reliable delivery. These upper 4 layers operate completely independent of physical wires. Their only concern is the logic and management of the message itself. At Layer 3, the network layer, segments are converted into packets. IP addresses are added to calculate the shortest route. Layer 2, data link, wraps packets into frames, applying MAC addresses for local node-to-node delivery. Finally, Layer 1 is the physical layer. This is where frames are transformed into raw binary bits, zeros and ones, so they can travel over a transmission medium like a copper cable or fiber optic line. This diagram illustrates parallel transmission at the physical layer. Both sender and receiver are connected by multiple data lines, allowing a complete group of binary bits to be sent simultaneously in one go. By contrast, this schematic displays serial transmission. Here, a single communication channel is used, requiring the binary bits to travel one after another in a sequential queue. The bottom layers act as the final translation point, converting abstract software instructions into tangible physical signals. The OSI model provides a pristine logical map, but it is purely a reference model. You cannot install it on a computer. The architecture actually running the internet is the TCP/IP suite, a pragmatic framework designed by the Department of Defense in the 1960s to connect hardware across ARPANET. This chart maps the two frameworks. The 7 OSI layers condense into 4 TCP/IP layers. Notice how the top 3 OSI layers collapse into a single application layer. At the bottom, data link and physical layers merge into the network interface layer. TCP/IP is concise because it was designed in reverse. The model was built to fit the protocols only after they were successfully tested in reality. The TCP/IP framework derives its functionality from the specific, actionable protocols running within its layers. This chart maps the protocols in each layer. In the transport layer, TCP guarantees reliable delivery, while UDP skips error checking for fast data. In the internet layer, IP routes packets, relying on ARP to map IP to physical hardware. The layered framework itself is passive. These protocols are the active software agents executing the network's rules. To see how these protocols automate massive tasks, look at the Dynamic Host Configuration Protocol, or DHCP, operating in the application layer. Devices use a 4-step DORA process to connect. First, the client broadcasts a discover message to find a server. The server responds with an offer of a temporary IP. The client sends a request to accept, and the server sends an acknowledgement, locking the parameters. Without this specific protocol executing its steps automatically, network administrators would have to manually assign IP addresses to every single desktop, laptop, and phone. Scaling a modern enterprise network would be impossible without it. This table contrasts the models. Row 6 highlights OSI protocols don't fit perfectly because the theory was written first. TCP/IP is coherent because protocols existed before the framework. Row 7 shows TCP/IP only supports connectionless communication at the network layer, whereas OSI accounts for both. The OSI model remains indispensable because it provides a universally understood taxonomy. It clearly distinguishes between services, interfaces, and protocols, giving engineers a shared language. Yet TCP/IP remains the undisputed functional standard. It is the actual code dictating how raw data flows across fiber optics and copper wire worldwide. True network engineering relies on both. You diagnose network behavior and conceptualize architecture using the pristine theory of OSI, but you execute the final operations with the rigorous practicality of TCP/IP.